All right, so 8.2, we're going to be testing the difference between means, except now we have independent samples with sigma 1 and sigma 2 unknown. So in section 8.1, we had sigma 1, sigma 2 known. Now it's unknown, okay? So to use this, we use the two sample t-test. You know, when we did this test in chapter 7 with one sample, when we did not know sigma, we used S, the sample standard deviation, instead of the population standard deviation. If you use S, you've got to use the t-distribution. All right, that's why it's the two sample t-test. In order to use the two sample t-test that tests the difference between the population means, we need to know sigma 1 and sigma 2 unknown. We need to know that it's random samples. We need to know that the samples are independent. And last, we need to have both normally distributed pops or N1, N2 greater than or equal to 30, okay? Or some combination. Maybe one is normally distributed and the other population is greater than or equal to 30. But it's some combination satisfied for both populations, all right? Or rather samples. So the test statistic is, again, x bar 1 minus x bar 2. The standardized test statistic is t equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 in parentheses over s x bar 1 minus x bar 2. Now the reason I write it like this is because there's two different versions here. Gets a little complicated. If I assume the variances are equal, so what does that look like? That means assume that sigma 1 equals sigma 2. Then my formula, my formula is difficult. So it's this big old square root, parentheses n1 minus 1, s1 squared, plus n2 minus 1, s2 squared, over n1 plus n2 minus 2. But that's not it. That's not all. Wait, there's more. Times the square root of 1 over n1 plus 1 over n2. The degrees of freedom for this version is equal to n1 plus n2 minus 2. Why is it minus 2 and not 1? Well, if you think about it, it's kind of like you've got two populations, an n1 minus 1 plus an n2 minus 1. And if you combine like terms, n1 plus n2 minus 1 is the same as minusing 2. Okay, so that's where that comes from. Now the second one, if the variances are not equal, so sigma 1 is assumed to be not equal to sigma 2. So at the very end of the problem, typically, they're going to have this part here, okay? If that's the case, then all we do is s1 squared over n1 plus s2 squared over n2. This looks very similar to the last section, except for instead of sigma, I have s here, okay? Now, the degrees of freedom is calculated a little bit different. It's the minimum. This is the smallest of two things, n1 minus 1 and n2 minus 1. So whichever one produces the smaller, then that's what the degrees of freedom is. It's the minimum of n1 minus 1 and n2 minus 1. So you pick the smaller of the two. Okay, you think about it, you always go for the smaller one. All right, So now what I'm going to do is I'm going to work two problems. I'm going to work one. The first one is going to be where the variances are not equal. And the second problem I'm going to do where the variances are equal. Okay? So results for a math test, random samples taught by two different teachers. This tells me there's two different populations, teacher 1, teacher 2, at the same school are given below. So the first teacher had an average of 473. The second teacher had an average of 459. All right. Can you conclude that there is a difference? So is there a difference in the mean math test scores for students of the two teachers? Assume normal distribution and the population variances are not equal. Okay, alpha 0.10. So everything that's highlighted is what's important information for us. Okay, so sigma 1 and sigma 2, I don't see that anywhere. I have sample standard deviations. That's all I have. So these are unknown. Okay. Random sample. So it's random samples and they're independent. Now, how do we know that they're independent? Well, I've got one teacher teaching a bunch of students and then another teacher teaching the other students. Okay, not the same students, right? Normally distributed, we assume normal distribution for both POPs. So we're ready to use the z-test. I'm sorry, the t-test. So I use the two sample t-test. Okay. All right. So what do I do here? Well, my ho and my ha. The ho, okay. What are we doing here? Can I conclude that there is a difference in the means? Okay, so maybe this is mean 1 and this is mean 2. So is there a difference? That's my claim. So the ho is the opposite of that. mu1 equals mu2. It's a two-tailed test. Okay, not equal to. The ha tells me the type of test. It's two-tailed. Okay. What about the t-value? How do I calculate the t-value? Well, it all depends on variances not equal to. So we go to the not equal to formula. Okay. So I take this. What do I know? In the ho, I assume these are equal, so that goes away. So I have this divided by that. So x bar 1 minus x bar 2 over the square root of s1 squared over n1 plus s2 squared over n2. So this gets me what? Gets me 473 minus 459 over 39.7 squared divided by 8 plus 24.5 squared over 18, and I square root that whole thing. When I type it in my calculator, I get roughly 0.922. Okay, so I have a t-value of 0.922. All right, that's my standardized test statistic. Whew. All right, critical values. Okay, so critical values, remember this is a t distribution. All right, we found the test statistic t equal 0.922. Okay, what am I given? I'm given alpha 10%. So to get my critical values, it's plus or minus because it's a two-tailed test. Alpha 10%. My degrees of freedom is the smallest of N1 and N2. minus 1, okay? So what is N1? N1 is 8, so 8 minus 1 is 7. And then N2, that's 18 minus 2, that's 16. So 7 is my degrees of freedom. That's smaller than 16. I'm sorry, why did I put minus 2 here? This should be minus 1, so that would be 17. But nevertheless, degrees of freedom is 7. Okay? So my degrees of freedom is 7. My alpha is 10%. I need to go to my T chart. So go into your T table. Degrees of freedom 7. Alpha, it's a two-tailed test, 10%. So 1.895. 1.895. So my T values, my critical values are 1.895 and negative 1.895. Those are my critical values. Okay. So I'm going to mark it over here. So this is T naught, and that's 1.895, and this is T naught, negative T naught, negative 1.895 over here. Now, where do I fall? Turns out I'm going to fall in the non-rejection region. This is in the non-rejection region. So what does that tell me? I fell to reject the hoe. Okay, why? Since T is between 1.9 or 895 and negative 1.895. Okay, we're in this region here, so that's the non-rejection region. So let me move this. Move that around a little bit so you can read that a little better. So that's negative 1.895 there. Okay. So what do I say? There is not. Why does it say is not? Because I said fail to reject. Enough. If it would have been reject, I would have put there is enough, but there is not enough evidence at alpha, a level of significance of 10%. To now, do I support or reject? My ha is the claim, so I support. If my ho had been the claim, I would reject. So there is not enough evidence to support the claim that the mean math scores for students of the two teachers are different. All right. So, maybe if you've got some teacher, he's given a whole lot more A's than another teacher might be. And one way to test to see, is this guy giving statistically more tests, A grades, than this other teacher, is you could run this type of test right here and determine, is there a statistical difference? Just looking at these two teachers, yeah, it looks like the grades are definitely higher for teacher 1 than teacher 2. But guess what? There's not enough evidence to support the claim. Okay? Can you conclude that there is a difference? So there's not enough evidence to say that there is a difference. All right? So we fell to reject the claim that they're equal. All right? So not enough evidence to support that claim. Okay, next problem. Out of the classroom and into the business world. Okay? A manufacturer claims, they make a claim that the mean driving cost per car, or the mean driving cost per mile of a sedan is less than that of the leading competitor. You conduct a study, you go out there and you randomly select 30 sedans from the manufacturer, and then you go out and you get 32 from the leading competitors. Okay? At alpha 0.05, can you support the manufacturer's claim? What's the manufacturer's claim? That the mean driving cost per mile of the sedan is less than that of the leading competitor. Assume population variances are equal. Okay? So we've got all of our information that's important highlighted. So sigma 1, sigma 2, unknown. All we know is the sample standard deviation. They're random samples, all right, randomly selected. We know they're independent because you've got your manufacturer claims and then you've got your leading competitor. They're competing against each other, independent. Now the ends, okay, N1, that's greater than or equal to 30. N2, that's greater than or equal to 30. So it barely makes the cutoff, but it makes it. All right. Now, when I run my test, I need my ho and my ha. So what's the ho and the ha? Well, the manufacturer claims that the mean driving, so I'm going to say mean mu1, and the competitor, we'll just call them mu2. Hopefully we're going to be better than our competitor, right? So mu1, mu2, just call it something, right? So I'm saying that the mean driving cost is less than, so the mean driving cost is less than the competitor's driving cost. We want the lowest cost. I mean, you want to be able to say, look, guys, buy our car, and not only are you going to save on our great prices, you're also going to pay less in the long run per mile. I mean, it's a pretty powerful advertising claim. But you can't just make claims that are untrue. That has to be supported by statistical data. Otherwise, you might get sued for false advertisement. And so that's my claim. And my null hypothesis is the opposite of this, greater than or equal to mu2. Okay. So what's going on here? What's going on? Let's do the test. Okay, let's try and do the test. This is going to be a booger. Maybe we should find the type of test first, okay? Because this one's going to be challenging. So the test, we look at the ha to tell me the type of test. It's pointing to the left, so that's a left-tailed. It's a left-tailed test. Okay, that's going to help. If it's a left-tailed test, the critical value T naught, we know alpha is equal to 0.05. That's given to us. But the degrees of freedom, okay, the degrees of freedom here, which one are we using? Variances are equal. So that means I use this one right here. Degrees of freedom, N1 plus N2 minus 2. That's when variances are assumed equal. N1 plus N2 minus 2. So that's 30 plus 32 minus 2. That's 60 total. So I go and I look up 0.05. One-tailed test. Degrees of freedom 60. So degrees of freedom 60. And then one-tailed 0.05, I go down 1.671. Okay. A very common mistake I see is I'll see students say T naught equals 1.671. Now, what's the problem with what they just did here? What's in the middle? 0. Guess what type of test it is, people? It's a left-tailed test, so we're on the left side for the t distribution. It's not like a z. To find the critical value is a little bit different. It's negative. You got to put the negative there, minus 1.671. Once you've got the negative, now we can work through the problem and see if our test statistic falls in the rejection region or the non-rejection region. So let's see if we can calculate it. T is equal to what? T is equal to x bar 1 minus x bar 2 over square root n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 2 times the square root of 1 over n1 plus 1 over n2. When I type this in my calculator, woo-wee, this is tough. 0.48 minus 0.51 divided by n1 looks like 30 minus 1 times s1 squared, 0.05 squared, plus 32 minus 1 times 0.07 squared over 30 plus 32 minus 2, square root 1 over 30 plus 1 over 32. That's a lot, and that's really challenging to type into your calculator, okay? But if you can do it, good for you. Negative 1.930, okay? Negative 1.930. Where does this fall? Where does this fall? Okay, so I'm going to make it red because I'm going to put red over here. With respect to my critical region, it falls over here. T equals negative 1.930. Okay, so I fell into the rejection region. So I reject the HO, reject H naught. Why? Since T was less than negative 1.671, right? It's in the rejection region, so that means it's less than that value, okay? So what do I say? There is not, note, there is. Why do I say there is? Because I wrote reject. There is enough evidence at alpha equal to 0.05 to support. Why do I use the word support? Because my claim is the ha. If my claim was the ho, then it would be reject there, but I use the word support. The manufacturer's claim that the mean driving cost per mile is less than the competitors. Wow, what a powerful statement that this statistician was able to say for this car company. Okay? So this manufacturing company can now advertise there's enough evidence. We're 95% sure, right? 0.05 alpha to support the manufacturer's claim that the mean driving cost per mile is less than our competitors. What a strong statement. All right, guys, good luck on your homework.